Let's look at the engine driving modern AI workflows, the agent skill specification file, commonly known as SKILL.md. This single file has a primary job. It instructs the AI agent on how to execute a specific task, heavily optimizing for system loading conventions and strict token limits. But it carries a second, entirely competing responsibility. It is the only document a human operator reads to determine if this capability actually fits their task and risk tolerance. Right now, the AI industry is obsessed with auditing that first duty. We run these files through static analysis and compliance benchmarks to ensure the model behaves correctly. Security pipelines aggressively scan the code for adversarial threats, like prompt injections, dangerous shell actions, and hidden data exfiltration. Yet these massive security pipelines completely ignore a distinct vulnerability: whether the human reading the file actually understands what the tool is going to do. A skill can pass every adversarial check with perfect scores, but if it leaves its user entirely unable to predict its operational behavior, it has failed. A recent study tackles this by borrowing from the description to permission fidelity tradition in app security. Researchers adapted this framework to measure human comprehension of AI skills as a hard, quantifiable metric. To do this, we must evaluate these files as user-facing capability disclosures, shifting the focus away from their role as executable instruction containers. Because a perfectly benign, non-malicious AI skill remains dangerous if the human operator misjudges its actual operational boundaries. The stakes are clearest in high-risk cybersecurity environments. Here, engineers regularly install skills to perform tasks they cannot independently verify, like deep threat intelligence extraction or CWE triage. In these environments, failures happen in two distinct ways. The first is an agent-side error, where the AI misuses a skill and generates a wrong answer. These execution errors are highly recoverable. The underlying system harness catches the failure, observes the bad output, and forces the AI to iterate and correct its next action. The second category is a user-side comprehension error, caused directly by reading a benign but opaque skill specification. In this scenario, the user misunderstands the tool's true coverage limits. They run the skill, and it produces a highly confident output that the user consumes without verification. This creates a false sense of assurance regarding the system's security posture, a failure mode that is completely invisible to system logs. This silent, compounding error is exactly why human comprehension must be treated as a load-bearing pillar of security, sitting right alongside malice checks. An AI's automated self-correction provides zero protection if the human operator blindly accepts a flawed output as verified truth. To see how well these specifications actually support users, researchers ran a deterministic, rule-based scan across 878 real-world cybersecurity skills. This chart shows the results of that scan, tracking 4 distinct textual comprehension anchors on the x-axis and their percentage of occurrence on the y-axis. The first anchor is operational basis, which simply states what inputs, evidence, and data sources the skill consumes. Naming what a tool eats is a default habit of technical writing. The second anchor is the output contract, which names the expected result schemas or specific finding fields. Next is boundary disclosure, detailing explicit scope limits, caveats, and false positive language. Admitting where a capability degrades or does not apply requires a deliberate discipline that nearly half of these authors skip. The final anchor is an example capability demonstration, providing a concrete sample output or runnable test case. Producing an example is rare because it demands building actual working material rather than just descriptive prose. But the most revealing metric is the percentage of skills that provide all 4 anchors as a coordinated package, just 2.3%. If these 4 anchors were written independently of one another, basic probabilities suggest nearly 6% of skills would have all 4. The reality of 2.3% proves these anchors are negatively correlated. The skills that carry examples are disproportionately not the ones that declare boundaries. The data suggests these documentation habits rarely overlap. Authors who prioritize boundary disclosures are often not the same ones providing concrete examples. The absence of coordinated comprehension support points to a template vacuum. Authors lack a standardized schema for what a complete capability disclosure should contain. We can see the exact mechanism of this failure by zooming in on a specific local test group, 6 skills designed to analyze DNS tunneling and command and control beaconing. When an engineer evaluates a tool, they perform a first local check, testing the skill against synthetic logs to verify its basic functionality before deploying it. Out of the 6 skills tested, only 1 provided a concrete sample output in its specification. That single example allowed the reader to clearly predict the expected output shape and construct a verification check directly from the text. The remaining 5 skills were fully functional, but their specifications abandoned the user. They left out crucial implementation details, relying on undocumented TSV parsers, implicit header expectations, and completely hidden arguments. Without an example, the verification process breaks down. The user is forced to stop reading the document and start reverse engineering the underlying helper code just to figure out how to run the skill. In this context, an example functions as a testable capability claim, establishing a baseline of operational trust. However, examples can mislead users if they lack fidelity. A selected fixture might exaggerate coverage, omit edge cases, or show an output structure that the helper code does not actually produce. Without a concrete, high-fidelity example, platform engineers are left with an impossible choice: either extend blind trust to a black box or perform exhausting code archaeology to verify the simplest task. A trustworthy ecosystem requires 3 measurable axes of evaluation. First, verify the skill is safe to install and free from malice. Second, prove it is effective to run, validating against compliance benchmarks. The third axis ensures it is understandable to choose, proven by explicit human comprehension anchors. Platform architecture teams can implement this third axis immediately at the point of intake. Because the 4 anchors rely on deterministic textual cues, they can be mechanically checked through automated pull request linting, requiring 0 model cost and scaling effortlessly. App stores and extension markets often outsource this trust to alternative ecosystem signals, like user ratings, reviews, and overall install counts. But those signals are easily manipulated attack surfaces. More importantly, a high rating completely fails to reveal a specific skill's required telemetry formats, output fields, and parser assumptions. We do have to acknowledge a strict boundary in this research. Deterministic scanning only measures the presence of textual cues. It does not measure the actual accuracy of a user's resulting expectation. The mandatory next step for the field is running controlled user studies to measure exactly how these specific anchors impact a reader's risk perception and verification ability. Until platforms audit comprehensibility with the same rigor as code security, the gap between a tool's actual behavior and the user's expectations will remain an unaddressed risk.